I am Naga Govindaraju, a distinguished engineer at Microsoft Azure. Our research is done with my collaborators Mark Rusinovich, Melur Raguraman, David Hepkin, Jamie Schwartz, and Arun Kishan, all from Microsoft Azure. Let me start with the motivation for our work. Public cloud providers such as Azure must regularly update the host OS. These updates are required to improve reliability by fixing bugs, enhance security by addressing vulnerabilities, and deploy new features for customers. For zero-day fixes, updates need to be done across the entire fleet within few hours. The updates may require host OS reboots and can lead to a significant customer impact, as reboots can expose bugs in the guest VMs and also applications lose their state. Our goal is to deploy zero-day updates on millions of servers without rebooting VMs. We want to build a generic mechanism to perform all virtualization stack updates, including rebootful and rebootless updates. Our mechanism needs to support all VM types, including ones that have hardware offloads. We need the update mechanism to achieve low VM blackout time in the order of tens of seconds. Lastly, updates need to be reliable and need to be resilient to failures when done at scale. There is significant literature over the last few decades on performing transparent updates. Broadly, they can be classified into four categories. Dynamic software update mechanisms perform live patching of processes that need updates. These systems require applications to be rewritten or recompiled and can be a challenge for third-party drivers. Failover systems use redundant systems to achieve high availability and are complementary to those improving VM availability, such as ours. Live migration is an elegant technique to migrate a VM from one server to another and can be used to update the host. However, live migration can be an issue for zero-day updates, as it requires time to create turn space and to migrate the VMs. Finally, there is independent research that preserves memory across a soft reboot or hypervisor reload and are the closest to ours. These techniques either do not handle virtualization stack updates or only handle hypervisor updates and not the entire host operating system. For a detailed overview on these techniques, please refer to the paper. Azure developed virtual machine preserving host updates, or VMFU, in 2012. At a high level, we suspend VMs in memory, soft reboot into the new OS, and resume the VMs. Note that the soft reboot step skips firmware post and BIOS initialization to improve the boot time. Next, we provide a detailed overview of our technique. We begin with an unpatched OS and use a control application to first load the new OS into memory. We then initiate a save operation for all of the VMs, which in turn pauses the vCPUs for the VMs and marks the memory pages for the VMs as in use in the new OS. At this point, all the devices on the VMs are closed, and we can update the virtualization device drivers as there are no handles on it. We then soft reboot into the new OS, restore VMs, and clear the restored pages in the database. Step 6 is optional for rebootless updates, and our workflow can be used for both hypervisor and host OS updates. Now we present details on hardware offloads. Hardware offloads is becoming increasingly common in Azure as we bridge the gap between bare metal servers and virtual machines. There are two primary ways to perform hardware offloads: single root input-output virtualization, also known as SRIOV, and discrete device assignment, also known as DDA. We handle the SRIOV network devices by falling back on a software shadow VNIC, VMFU, and then enable the virtual function for the SRIOV VM. During the period of the software fallback, there is a short drawn out for the VMs. DDA devices are harder to handle as there is no software fallback. The device is exposed to the VMs, and we need to handle DMA and interrupt processing across the update. We solve this issue by keeping the IOMMU active during a reboot. That helps us maintain the DMA and interrupt remapping capabilities in IOMMU across the reboot. We then inject interrupts for each device in the VM, as there is a small period of time when the hypervisor is offline and may miss some interrupts. The injection of the interrupts allows for the device drivers inside the guest VMs to process any missed interrupts during this time period. We now show a demo of VMfoo in action on an Azure server hosting a GPU DDA VM. On the right side of the screen, we have a 3D mark benchmark running in an Azure VM. This Azure VM has 4 NVIDIA Tesla T4 GPUs as shown over here. We also have a script running inside the VM to measure the blackout time. On the left side of the screen, we have the Azure host running the VM. We will now do a rebootless update of the storage virtualization driver on the host. The update is complete and the blackout time experienced by the VM is around 1 second. We also notice that the benchmark is running fine with no issues. As I mentioned earlier, one of our goals is to achieve low VM blackout time in the order of seconds. This is necessary to have no impact on applications running on VMs. VMfoo blackout time is dependent on 3 main factors: time to soft reboot, time to close the VM devices, and time to preserve VM memory. In the next few slides, we provide a deep dive into these 3 factors. The first factor that impacts blackout is the reboot time. It is important to optimize the reboot time as it impacts the blackout for all the VMs on the host. As shown in this graph, the reboot process is very I/O intensive, primarily reading hundreds of megabytes of data, and it can take tens of seconds on hard disks. Our solution to improve the reboot time is to cache the reads and writes using a file system driver in memory. We also preserve the cache across reboot using the same techniques used for preserving VM memory. We show a log scale plot of the boot time without KSR, known as normal reboot, with KSR, and with fast reboot KSR using our caching optimization. As can be seen, the normal reboot highlighted in the color blue can take several minutes to complete. KSR highlighted in the color gray cuts down the boot time to 20 to 50 seconds. With our caching optimization highlighted in the color yellow, we are able to boot within 8 to 10 seconds on all of our SKUs, including the ones running on hard disks. The second factor impacting reboot time is the time to close all the devices. In our technique, soft reboot can only proceed after all VMs close their devices. As a result, any straggler device can impact blackout time for all VMs on the host. The straggler device close operations occur if the VM storage backend is offline or the network connectivity has issues. Our solution is to fast close the devices. We serialize the in-flight IOs during VM save and pin their status. We can then close the devices and immediately soft reboot, eliminating stragglers, impacting blackout time for the VMs. Prior to restoring VMs, we replay their serialized IOs. Any straggler will only impact their blackout time. To further improve blackout, the serialized IOs are preserved in memory across the reboot using the same techniques that we use to preserve VM memory. We ship the fast close feature known as storage resiliency in Windows Server 2016. Another important factor that determines blackout time is the time to preserve VM memory pages. Windows Memory Manager uses a linked list to maintain the free regions. This means that marking the pages as in use is order n square, where n is the number of memory runs for the VMs. On systems with low fragmentation, n is small, but on highly fragmented systems, n can be in the order of hundreds of thousands. Similar to the issues in closing devices, straggler VMs increase blackout for all the VMs on the host. Also, since the hosts do not reboot and VMs are created and deleted on a continuous basis, the host and VM memory can be very fragmented. So the n-square algorithm can take hundreds of seconds. One solution can be to fix the memory manager data structure to optimize for VM preservation. But such changes are fundamental and introduce trade-offs to other scenarios that memory manager supports. We therefore need a order n algorithm specific to VMfoo. To do so, we modified our algorithm to use a sorted list for the VM memory runs and leveraged insertion sort. For more details on this, please refer to the paper. With these changes, as can be seen from the graph, we are able to preserve the memory within 4 seconds on even very fragmented systems. This graph highlights the number of runs observed on millions of servers over the last year. As can be seen, some servers are very heavily fragmented with over 1 million runs. Our technique is able to preserve and restore memory within 4 seconds, even on the most heavily fragmented systems. Also, our production results highlight close to linear performance with the number of runs, as can be seen from the graph. When we deployed VMfoo into our pre-production rings, we observed around 5% failures in soft reboot. These failures are root caused to 2 primary reasons. First, memory range dependencies for certain drivers are not satisfied, as those ranges are now occupied by memory saved across reboot. The second class of failures correspond to contiguous memory allocation failures. These are due to severe memory fragmentation, causing those allocations to fail. We address these issues by partitioning the host and guest memory ranges. We use the lower memory ranges for the host, as the host may have legacy drivers requiring those ranges. Memory partitioning has several benefits, as it reduces fragmentation and allows for consistent and fast VM and host startup. It also eliminated the failures we noticed during the soft reboot. We deployed our system in 2015 across all of Azure using a code base based on Windows Server 2016. We enlightened many drivers to support VMfoo, and they are shown in the table on the right. Some of the drivers, such as networking and storage virtualization drivers, are updated rebootlessly. However, others, such as PCI.sys, required reboots. As we noted, reboots are disruptive to customers. To avoid reboots, we needed a way to perform VMfoo to enable VMfoo. We solved this problem by leveraging hot patching. At a high level, we hot patched the shutdown routines of the drivers to preserve their state. And then we leveraged VMfoo to update the drivers. The overall rollout took 3 months to complete. We now show a demo of our rebootful updates on an Azure server. Let me switch to the demo. We now have 2 remote desktop windows on the screen. On the left, we have the host to be updated. On the right, we have the VM hosted on this server. Inside the VM, we have a script running that is monitoring the time drift to measure the blackout time. We also have an application downloading a large file inside the VM. Now let's update the host and observe the application behavior. As we discussed earlier, the first step is to load the kernel into the memory. This step can take several seconds to complete. During this time period, the VM is up and running, as can be seen over here. Once the kernel is loaded into the memory, the next step is to fast save the VM and then perform a soft reboot. When a soft reboot is performed, the remote desktop connection to the host will terminate as shown over here, and the application pauses. Let us now wait for the update to complete. It takes a few seconds for this update to complete. The update is now complete and the application resumed. We can also see that the blackout time observed by the VM is around 11.7 seconds. We now present an analysis of our technique in production. The graph on the right highlights blackout time in production during the last year on millions of servers and tens of millions of VMs. As can be seen in the graph, the blackout time for rebootless updates ranges from few seconds to at most 9 seconds. For reboot full updates, the blackout time ranges from around 12 seconds to at most 20 seconds. The difference in the blackout time between reboot full and rebootless updates is around 8 to 10 seconds and is due to the soft reboot. On an average, we perform 2 to 3 rebootless updates and at most 1 reboot full update per year. We also notice a low failure rate of around 0.1%. These failures typically correspond to hardware failures. So far, we have discussed how we can perform fast updates and roll out quickly for a 0-day. However, fast rollouts can introduce significant risk due to potential for regressions in the payload. Examples of these regressions include memory leaks where the memory is allocated and not freed, driver hangs where reference counts can mismatch causing devices to not close at all, and even host crashes due to bugs such as access violations. The failures can manifest as VM allocation failures as the host memory leak to the extent that new allocations fail, VM stop failures as the devices do not close, and appear as side effects in control plane and data plane operations that is hard to pinpoint to the exact failure. Moreover, the issues can take many days to accumulate, can be workload dependent, and show only on a small fraction of the fleet, making it hard to identify. Further, once issues are identified, fixes take time to develop, validate, and deploy. We therefore need to balance the risk by building a resiliency mechanism in addition to update mechanisms for 0-day patching. As with updates, our goal is to mitigate the issue without rebooting the VMs. At a high level, we use VM-foo and clear the offending host state. There are some key differences in our resiliency strategy. First, there is no new OS payload. We therefore use the same OS to register the VM memory. Second, all VMs may not save as there may be some threats for the VMs that are deadlocked, for instance, in driver hangs. We therefore do a best case effort to preserve the VMs. For the VMs that fail to save, we treat them as VM failures, but isolate the failures only to those VMs. Thirdly, we need to include debug information on which device failed to close or which component leaked memory in order to debug before we clear the state of the host. Rollouts to production proceed in a staged manner even for 0-day updates. 80% of issues are proactively identified in pre-production environments. These issues are fixed before the rollout proceeds broadly. We mitigate the remaining regressions using our resiliency strategy using VM-foo. It not only improved the quality of 0-day updates, but also all rollouts benefited from it. Our technique has few limitations. It is primarily designed for updates. It cannot be leveraged for other data center scenarios such as hardware decom, load balancing of resources, and hardware failures. Live migration may be a better fit for these scenarios. Also, few applications may not tolerate a pause. For these cases, we leverage scheduled events 15 minutes prior to VM-foo. We also provide an option to opt out and allow the customer control on when to take updates on a dedicated host. In summary, we presented a fast in-place update mechanism for upgrading Azure hosts without rebooting VMs. Our techniques are designed to handle all VM types, including the ones with hardware offloads. We also presented several optimizations to improve reliability and blackout time. We designed our optimizations to account for stragglers to minimize the long tail. We applied our techniques in a large-scale public cloud with millions of servers and VMs. We achieved low blackout time. We applied the technique to several 0-day cases such as Spectre and Meltdown, and deployed across the entire fleet within few hours. We designed resiliency using VM-foo to balance the risk of regressions with fast rollouts. For any questions or feedback, please feel free to send an email to markers@microsoft.com or nagaji@microsoft.com. Thank you.